Hi, my name is Shikhar and I will be presenting neural dynamic policies for end-to-end sensorimotor learning. This is joint work with Mustafa Mukaddam, Abhinav Gupta, and Deepak Pathak. Consider a robot trying to catch a ball. It needs to reason in the trajectory space. That is, it needs to know when and where it should intercept the ball. But it also has to reason about its momentum and forces that it applies to its fingers so that it can catch the ball smoothly. Hence, we need reasoning about both kinematics and dynamics. In contrast, current methods in deep robot learning often output actions at each time step and do not reason in trajectory space. Furthermore, they operate in raw action spaces, outputting end-effector positions or torques at each time step. This is probably fine for quasi-static tasks like planar pushing, where an object is on a table and a robot can take as much time as it wants to take the next action, but not for tasks that involve more complex dynamics, such as catching, where the robot has to act fast to model the trajectory of the ball. In this talk, I will present how to build policies that directly reason in trajectory space. Many naturally occurring phenomena are dynamical systems that can be described by a set of nonlinear differential equations. For example, the motion of fluids, the flow of heat, or how planets move around the sun. So can we use the same formulation that is used to describe the movement of planets to describe the motion of a robot? Indeed, people have thought about how to use such structure for defining trajectories in classical robotics. For instance, the seminal work on dynamic movement primitives, or DMPs, which are a second-order dynamical system, has been very successful in allowing robots to perform real-world tasks such as table tennis, pancake flipping, or letter writing. These DMP-based methods can handle dynamic tasks really well, and they can reason in trajectory space. However, in order to obtain this parameterization, most approaches require dense supervision, usually coming from structured human demonstrations, and they are very sensitive to hand-engineered parameter tuning. The second and more important drawback is these are very difficult to generalize to high-dimensional inputs, for example, images. In contrast, deep reinforcement learning methods can learn from high-dimensional inputs pretty well. Furthermore, these methods are also able to learn from weak supervisions, such as rewards. However, unlike DMPs, they only reason at each time step and not at the full trajectory. And they have difficulty with dynamic tasks. So how can we bridge the gap between these two paradigms? In current methods, a state input is given to a black box network which outputs an action that is executed in the environment. In contrast, instead of the black box network, we propose embedding a dynamical system inside the policy. We call our method neural dynamic policies. We embed the dynamical system that describes dynamic movement primitives which govern the policy output. The system is embedded in an end-to-end differentiable manner. Given an input state, a network phi is used to obtain parameters for the dynamical system. Given a choice of coordinate system, such as either joint angles or end-effector positions, let this robot state be y. Given a desired goal state g, the behavior of this agent is represented as the second-order differential equation in y. The construction of the system allows for critical damping and smooth convergence to the goal state. In short, this makes sure that the trajectory is physically realizable. But we might want to represent different trajectory shapes with this system. This is achieved by a nonlinear forcing function f, which captures the shape of the trajectory. A common practice in the DMP literature is to represent f with radial basis functions. The combination of these basis functions gives different weights to different parts of the trajectory, overall allowing them to represent arbitrary shapes. The weights of the basis functions w are output by the neural network. These allow neural dynamic policies to generate different trajectory shapes. This set of nonlinear differential equations induces a smooth trajectory distribution that acts as an attractor towards the goal state. A forward integrator then uses these DMP parameters and outputs a trajectory to follow. We can then use this trajectory to output actions for the robot to execute in the environment. Embedding such structure allows our policy to reason in the space of physically plausible trajectory distributions, while maintaining the benefits of end-to-end learning methods as well. Before I go into the algorithm and results, let me show you some intuition about what NDPs might be capturing. Consider a graph of a robot's joint positions versus the rollout length. Given a starting joint position and a goal shown in green, here are the trajectories output by a vanilla RL policy and an NDP. The blue line is a trajectory taken by a vanilla RL policy. Note that this shows a noisy and jerking looking path to the goal, since the action is being decided at each time step. On the other hand, the red trajectory, governed by an NDP, shows a smooth convergence to the same goal. We make some simple and minimal modifications to a typical reinforcement learning algorithm in order to incorporate NDPs. Implementation details can be found in our paper, and we have released our code as well. Now, let's look at some results. We test our method in both imitation learning and reinforcement learning. Let me begin by talking about reinforcement learning results. We test our method in the reinforcement learning setting on dynamic tasks like throwing and picking, and on quasi-static tasks like pushing, faucet opening, soccer, and even a joint multitask benchmark called MT50 from the meta-world set of environments. We compare NDPs against state-of-the-art baselines, including methods that reason at a trajectory level and vanilla RL approaches. We can see that our method, shown in red, outperforms several prior approaches, either in terms of absolute performance or sample efficiency. But as discussed earlier, current approaches have difficulty in reasoning about dynamic tasks. We can see that NDPs, on the other hand, give a very strong boost on dynamic tasks, such as throwing and picking, while being comparable or better for quasi-static tasks. We present some visualizations of our method against a multi-action PPO baseline. On the picking task, as we can see here, our method not only has a better performance, but also produces smoother and more physically meaningful trajectories. This can be a strong benefit when learning in the real world. The same story holds for throwing, another dynamic task. Now, let's look at some imitation learning results. For this setting, we consider the same continuous control tasks as the reinforcement learning experiments. We see that NDPs outperform the neural network baseline in most tasks. I will now present results where we learn NDPs from visual inputs. We present results on a toy digit writing task. Given a desired image, the goal is for a 2D robot to draw the digit. We present the results of our method, NDP, and compare them to a vanilla CNN baseline and to previous work that learns DMPs, which we call CNN DMP. We can see that NDP produces a smoother and more accurate reconstruction of the desired trajectory. When the task is more difficult, such as drawing an 8, we can see that the baseline methods struggle a lot, while NDP is able to capture the digit shape quite well. In conclusion, we present a way to embed the structure of dynamical systems into deep network policies. We call these neural dynamic policies, or NDPs. These are inspired by work done on dynamic movement primitives and naturally occurring phenomena which can be described by dynamical systems. NDPs can reason at a trajectory level, and they produce physically meaningful outputs, while keeping all of the advantages of deep learning methods, such as the ability to learn from visual data and the ability to learn from weak supervisions, such as rewards. We show that NDPs can be easily incorporated in end-to-end learning setups, such as reinforcement learning or imitation learning. We can see that NDPs show strong performance in both such settings, especially in dynamic tasks. Thanks for watching this talk. For more information, we encourage you to visit our poster and our website. Our code is also available on GitHub. Finally, I would like to thank my co-authors on this project.